Module 4, Lecture A, Working with Lists. By the end of this lecture, you will be able to create and manipulate Python lists using indexing and slicing, use common list methods to add, remove, and search for elements, and iterate over lists with loops to process each element. Python List Basics. List Literal Basics. A list is an ordered container that holds a sequence of related items under a single name. When you write a list directly in your code, you are creating a list literal, which defines both the items it contains and their order at that moment. This initial definition serves as the starting point for later operations, such as using positions to access specific elements or slicing to work with parts of the list. In this way, the list literal sets up the data so it can be easily accessed and modified later. List literals preserve the order of elements exactly as you define them, which is crucial when the sequence matters, such as days of the week or hourly temperature readings. Because lists are ordered, you can access or change items based on their position. This makes them ideal for tasks where sequence is important, like time series analysis or managing playlists. Unlike collections that ignore order, lists support workflows where the order of steps must be maintained. List literals let you store data in a flexible way, either as uniform values like exam scores, or as mixed values such as a student's name, ID, and grade in one place. They can also contain other lists, which supports more complex structures like daily schedules. By defining these list structures directly in your code, you create a clear framework for how data is organized. This makes it easier to access, slice, and transform elements, which is especially important in scientific and business applications. Python code. List Literal Basics. In this section, we will create simple list values using everyday examples and see how they work. We will show that lists preserve the exact order of elements as you write them, so the printed output matches that order. You will also see different kinds of list values and what they look like when displayed. If any extra software is required, you may need to install the appropriate library first. We create a shopping list that holds several grocery items, such as milk, eggs, bread, and apples. This list is made up of strings, each representing one item. In Python, lists keep elements in the order they are added, so the items stay in that sequence. This ordered structure makes it easy to organize the groceries and to access specific items by their position in the list. We create a list of temperature readings in Fahrenheit that contains 4 integer values, 68, 70, 69, and 72. This list stores the temperatures in the order they were recorded. Keeping them in a single ordered collection makes it easy to access, analyze, and modify the temperature data later in the program, while preserving the original sequence. In this example, we build a list called movie_info that stores different kinds of data about a movie in one place. It includes the title, Inception, the release year, 2010, the rating, 8.8, and the age rating, PG-13. This shows that a single list can hold mixed data types, such as text and numbers, while keeping all the related information together. Because of this, lists are a versatile way to organize connected pieces of data in a single structure. We use a nested list to represent simple schedules for 2 days, where the outer list holds one inner list for each day. The first inner list represents Monday with its activities, and the second represents Tuesday with its own tasks. This structure keeps each day's activities grouped together and preserves the order in which they occur, making the schedule clear and easy to understand. We begin by printing the entire shopping list so we can see its structure and contents. This lets us check that all the grocery items are present and appear in the correct order. By viewing the list directly, we confirm that it still matches the sequence in which the items were originally defined. This line of code prints the list of temperature readings in Fahrenheit. It uses the print function to show a label followed by the values stored in the temperature list. This output lets you verify that the numeric values are preserved correctly and appear in the same order in which they were defined. This code prints the contents of a list called Movie Info, which stores different types of data about a movie, such as its title, release year, rating, and age rating. By displaying the entire list at once, you can quickly see all these pieces of information together. This helps you confirm that the list contains the correct values in the right order. The code prints a schedule that is stored as a nested list, where each inner list represents one day's activities. When you display this schedule, you can clearly see both the overall structure and the specific items in each day's list. This confirms how the nested list keeps related activities grouped and organized by day. This example shows how to build a sentence by taking specific items from two lists. It uses the first element of a shopping list, which is milk, and the first element of a movie information list, which is Inception. A print statement then combines these elements into a complete sentence that says, "You bought milk and watched Inception." This illustrates how to retrieve individual list elements and use them to create meaningful output. This material explains how Python list literals can be created and used to organize different kinds of data. It describes lists that hold grocery items, temperature readings, mixed information about a movie, and even nested lists that represent simple schedules. When the script runs, it prints these lists to show that they keep elements in the order they were defined. It also builds a sentence by pulling out specific items from the lists, demonstrating how to access individual elements. Overall, it highlights that lists are a flexible and straightforward way to store and retrieve ordered data in Python. Accessing list items. In Python, lists store items in a specific order, and you access each item by its position, called an index. Indexing starts at 0, so the first item is at position 0, the second at 1, and so on. This zero-based system may feel unusual at first, but it becomes natural with use. For example, in a list of weekdays, index 0 would be Monday and index 1 would be Tuesday, and you can use these positions to retrieve numbers, text, or more complex objects from the list. In Python lists, you can access items from both the beginning and the end using indexing. Positive positions count from the start, while negative positions count backward from the end, with the last item at -1, the second to last at -2, and so on. This lets you work with elements flexibly without knowing the list's length, such as getting the first sensor reading with a positive index and the latest reading with a -1. In a similar way, a customer order system can quickly fetch the most recent order using a negative index. Understanding both forward and backward indexing gives you precise control over which list elements you access. When working with lists in Python, it is important to understand what happens if you try to access a position that does not exist. Going beyond the list's boundaries causes an error, which is useful because it reveals incorrect assumptions about the list's size. To avoid these errors, keep track of the list's current length, especially when positions are calculated automatically, such as in financial processing. You can do this by checking the length, using loops, or using slicing so you stay within valid positions. A clear grasp of how positions map to items will make your list operations more reliable and easier to manage in real-world programs. Python code accessing list items. In Python lists, you can access items using positive indexes that start at 0 for the first element and increase as you move forward through the list. You can also use negative indexes, which start at -1 for the last element and move backward from the end. Both positive and negative indexes must stay within the valid range of positions in the list. If you try to access a position that is outside this range, Python raises an index error to indicate that the index is invalid. This line in the script is simply a placeholder to remind you to install any libraries the code might need. In this particular version, no external libraries are actually used, so nothing needs to be installed right now. However, including such a reminder is common practice when sharing code, especially if the script may later be expanded to use additional features that depend on external packages. We begin by creating a list called Workweek Days that contains the days from Monday through Friday in order. This list serves as a simple example to show how we can access items based on their position. Using it, we can demonstrate indexing from the beginning of the list as well as from the end. Setting up this list provides a clear way to explore how indexing works in Python. In this example, we access the first element of a list by using an index of 0. Python lists are 0 indexed, which means the first item is at position 0, the second at position 1, and so on. Using an index of 0 returns the first item in the list, such as Monday in a list of workweek days. This is the standard way to get elements from a list based on their position starting from the beginning. In this example, we access the third day of the workweek by using an index of 2 because Python lists start counting at 0. That means index 0 is the first element, index 1 is the second, and index 2 is the third. Using this index is a simple way to retrieve a specific item from a list when you know its position. Once we store this value in a variable, we can easily use or modify that particular day later in the code. In this example, we use a negative index to access the last item in a list of workweek days. In Python, negative indexing counts from the end of the list, so an index of -1 refers to the final element. This lets us get items from the end without knowing how long the list is. Here, using -1 returns Friday from the list. Using a negative index of -2 lets us access the second to last item in a list called workweek days. negative indexing counts from the end of the list instead of the beginning. In this example, it returns Thursday, which is the second last weekday in the list. This approach is convenient because it avoids having to calculate the corresponding positive index. This line of code prints the first day of the workweek by accessing the list element at index 0. In Python, positive indexing starts at 0, so index 0 refers to the first item in the list. The print statement includes a label to make it clear that the value shown is the first day, helping demonstrate how positive indexing works in a simple, readable way. This example shows how positive indexing works in a Python list. Because lists use zero-based indexing, the element at index 2 is actually the third item. When we access the list at index 2, we retrieve the third day of the workweek, which is Wednesday. This value is then printed, demonstrating how to access elements starting from the beginning of a list. In this example, we print the last day of the workweek by using a negative index. In Python, an index of -1 refers to the final element in a list. This lets us access items from the end without knowing how long the list is. As a result, the code prints Friday, showing how negative indexing provides a simple way to reach the last element. This line uses a negative index to print the second to last day of the workweek. By using -2, it selects the second element from the end of the list, which is Thursday. This shows that negative indexing lets you count backward from the end of a list, instead of calculating positions from the beginning, giving you a flexible way to access elements. We set a variable to the value 4 to indicate which position in the list we want to access. This value represents the index we plan to use. By doing this, we can later check whether this index is within the valid range of the list. This helps ensure we access list elements safely and avoid errors from using an index that is outside the list's bounds. Before accessing an element in a list, we first check that the index is valid. This means confirming that it is 0 or greater and still less than the total number of items in the list. By enforcing this range, we make sure the index actually refers to an existing element. This simple check helps prevent errors that occur when trying to access positions that do not exist in the list. We print a message to show that we are safely accessing an element in the list. This is only done when the index is within the valid range of the list. In this example, we access the element at index 4 in the list of workweek days. By staying within the valid range, we avoid errors that occur when trying to access an index that does not exist. The code starts by using a try block to handle possible errors that might occur while it runs. This is especially helpful for catching exceptions such as an index error, which happens when the program tries to access a list position that does not exist. By placing risky operations inside a try block, the program can attempt them safely and respond to any errors in a controlled way. This helps prevent the program from crashing unexpectedly and allows it to fail more gracefully. In this example, we try to access the element at index 10 in a list that only has 5 workweek days. Because that position does not exist, the index is out of range. In Python, this causes an index error, which is a common exception raised when you reference a list position that is not valid. The key idea is that you must always make sure your index falls within the actual size of the list. In this example, we prepare for the possibility of trying to access a list position that does not exist. We use a try except block so that if Python raises an index error, the program does not crash. Instead, the except part catches this specific error and prints a message explaining that an index error occurred, along with details about the problem. This lets the program handle the error gracefully and provide clear feedback to the user. This code uses a try except block to handle errors without crashing the program. When it tries to access an element at index 10, which is outside the list's valid range, an index error occurs. The except block catches this error and prevents the program from stopping. It then prints a message that an index error happened, along with the system's explanation that the requested index is out of range. This script shows how to access items in a Python list using both positive and negative indexes. It uses a list of weekdays to demonstrate getting elements from the beginning and from the end of the list. The script also checks whether an index is within the valid range before accessing it, which helps avoid errors. Finally, it deliberately tries to use an index that is too large, catches the resulting index error, and prints a helpful message, illustrating basic error handling for list operations. List slicing basics. Slicing in Python lets you quickly take a range of elements from a list by choosing where to start, where to stop, and optionally, how many items to skip. The slice ends just before the stopping position, a common half-open rule in Python. This operation returns a new list with the selected elements and does not change the original list unless you explicitly assign the slice back into it. Overall, slicing provides a concise and consistent way to work with parts of list data. In Python, slicing is flexible because you can leave out the starting or ending positions. If you omit the start, the slice begins at the first element, and if you omit the end, it continues to the last element. This makes it easy to select ranges, such as from the third item to the end, or just the first few items. You can also use negative indices to count from the end of the list, which is helpful for working with recent items, like the last week of temperatures, messages, or transactions without needing to know the list's exact length. Using a step value in slicing gives you extra control over how you select elements from a list. With a step greater than 1, you can pick every second, third, or nth item, which is useful for sampling or forming alternating groups. A negative step reverses the list, helping you view items in reverse order, such as recent visits or transactions. By choosing the start, end, and step carefully, slicing becomes a powerful way to reshape and analyze list data efficiently. Python code. List slicing basics. This section explains how to slice lists using a starting position, an ending position, and an optional step value. It shows that when you leave out the start, the slice begins at the first element, and when you leave out the end, it continues to the last element. You also learn how negative indices count from the end of the list. Finally, it illustrates how using a negative step lets you create reversed slices of the list. This line is simply a placeholder comment reminding developers to install any needed external libraries before running the script. It signals that the code may depend on packages that are not part of the standard Python library. Including such a comment is helpful when sharing code so others know they might need to install additional dependencies for the script to work correctly. We begin by setting up a list of daily temperature readings measured in Fahrenheit, with each number representing the temperature for a specific day. The values are stored in the order they are entered so we can easily access and modify them later in the program. This list serves as the basic data structure we will use to demonstrate different ways of slicing and working with lists. First, we display the full list of temperatures stored in the Fahrenheit temperature variable. Printing this list lets us see all the values at once. This simple check helps us confirm that the list contains what we expect before we start working with smaller parts of it using slicing. We take a list of temperatures and slice it from index 2 up to, but not including, index 5, which selects the third, fourth, and fifth values. This subset is stored in a new variable and then printed with a label that explains which indices it represents. The example shows how list slicing lets you access a specific range of elements within a larger list. We create a slice of the temperature list that goes from the beginning up to, but not including, index 3, which gives us the first 3 elements. We then print these values to see the temperatures for the initial days. This method is useful for quickly accessing a subset of a list when you want to start from the first element without specifying a starting index. We create a slice of the temperature list that starts at the 5th element and continues to the end by using the index that corresponds to the 5th position and leaving the end open. This slice is saved in a variable that represents the last days. We then print this variable to display the temperatures from the 5th day onward, giving us a focused view of the later part of the list. Negative indices let you access items starting from the end of a list instead of the beginning. By using -3 as the starting index, you can quickly select the last 3 Fahrenheit temperatures without working out their positive index positions. This makes it easy to grab the most recent temperature readings. You then print these last 3 values to the console to view them. Just sample every second temperature from a list. You can use list slicing with a starting index of 0, so you begin at the first value. Then you set the step size to 2, which tells Python to pick every second element, and skip the ones in between. This creates a new list containing only the temperatures taken at every second position. Finally, you display this new list to see the sampled temperatures. To reverse a list of temperatures in Python, you can use slicing with a negative step value. This tells Python to start from the end of the list and move backward toward the beginning. The result is a new list where the temperatures appear in the opposite order from the original. You can then print this new list to view the temperatures in reverse. This script uses a list of daily temperatures in Fahrenheit to demonstrate several list slicing techniques. It first shows the full list, then takes a slice from the 3rd to the 5th value to illustrate that the end position is not included. It also shows how leaving out the start index gives the first few values, and leaving out the end index gives all values from a certain point to the end, using negative positions. It selects the last 3 temperatures to show how counting from the end works. Finally, it samples every second temperature and reverses the entire list with a negative step, demonstrating how slicing can both skip elements and reorder the list. List, methods, essentials. Appending list items. When managing data collections, a basic operation is adding new items to the end of a list, similar to placing another book at the far right of a shelf. This is especially useful when you do not know in advance how many items you will have. For example, each new survey response or incoming sensor reading can simply be appended to the existing list. Appending in this way lets you accumulate data over time without reorganizing the entire collection. Appending lets you build lists gradually as new data arrives while keeping the original order. It is like adding items one by one to a growing collection, which is useful in areas such as research or project management. Because each new item is added at the end, the sequence reflects when or how items were discovered or prioritized. This preserved order is important for clear organization, later analysis, and accurate reporting. Appending means adding new, relevant items to the end of a list so you can build up data over time while keeping its order. It is widely used in tasks like processing server logs or online transactions, where only important entries are added for later analysis. In education, you might append student submissions to a list to generate feedback. And in interactive systems like chat applications, appending helps maintain a complete history of messages or edits. Understanding appending is key to extending lists in a controlled, incremental way and constructing more complex data collections. Python code, appending list items. This lesson shows how a Python list grows as you append new items to it. You start with an initial playlist, then add one element at a time using the append operation. After each append, you display the current contents of the playlist so it is clear how the list changes. By the end, you can see the list expanding step by step as each new element is added. In this part of the code, we point out that no external libraries are needed because we only rely on Python's built-in features. As a result, the program stays simple and self-contained. It can run in any standard Python setup without installing extra packages or doing additional configuration. We begin by setting up an empty playlist that will hold song titles as we find them. Starting with an empty list gives us a flexible container that can grow over time. As new songs become available, we simply add each title to this list. This makes it easy to build and manage a collection of songs efficiently. We begin building our playlist by adding the first song using the append method, which places a new song title at the end of the list. In this example, we add Song A, called Morning Drive, as the starting point of our collection. This shows how a playlist can grow dynamically as we discover and append new songs. We add a new song to the playlist by calling the append method on the playlist list, which takes the song title Song B, Coffee Break, and places it at the end. This automatically increases the size of the playlist. Using append lets us keep track of songs in the order we discover them. We now add a third song to the playlist by using the append method to include Song C, called Evening Walk. This operation places the new song at the end of the existing list. It shows how the playlist can grow dynamically as we continue to discover and add more songs over time. The code prints the current playlist after 3 songs have been added to show its order and contents at that moment. This display lets you see how the list has changed with each addition. It highlights how lists in Python can grow over time and helps you visualize this dynamic behavior in a simple way. In this example, we expand our playlist by adding another song called Song D, Midnight Highway, to the existing list. This shows that Python lists are dynamic, meaning you can keep adding new items as needed. Each time you append a new song, the list automatically grows to include the new entry without any extra work from you. This code adds a new song title to the end of an existing playlist, showing that a Python list can grow dynamically. By appending the song called Song E, Weekend Road Trip, it illustrates that you can keep adding items as needed. The list preserves the order in which songs are added, so new entries appear after the existing ones. We start by printing a message to signal that we are about to show the final playlist order. This prepares the listener to see the complete list of songs that have been added. The playlist reflects the order in which the songs were discovered. This step neatly summarizes and presents all the collected data in a clear, organized way. We loop through the playlist using a function that gives us both the position number and the song title for each item. The positions start at 1, so they are easier for people to read. For every song, we print its number, followed by a dash, and then the song title. This produces a clean, ordered list of songs that shows the sequence in which they were added to the playlist. This example shows how a Python list can grow as new items are added. It starts with an empty playlist meant to store song titles, then adds 5 songs one by one. After the first 3 songs are added, the current playlist is printed to show the order in which the songs were stored. 2 more songs are then added, and the final playlist is printed with each song shown in its position. Overall, the script illustrates how lists in Python provide a simple and flexible way to store and expand collections of data dynamically. Removing list elements. When working with data collections, it is just as important to know how to remove items as it is to add them. Lists change over time as items become outdated or irrelevant, such as withdrawn students or completed tasks. You need reliable ways to remove elements by their position, by their value, or in groups so the collection stays accurate. Understanding these removal strategies helps you avoid mistakes like deleting the wrong item or leaving the data in an inconsistent state. When removing elements from a list, you can either target them by their position or by their value. If you know the index, you remove an item based on where it sits in the list, while removing by value means taking out a specific item that matches what you are looking for. These approaches are often combined with conditions, such as filtering out data that falls outside an acceptable range. Having a clear strategy for whether you are using positions, values, or conditions helps you manage list data effectively. When removing items from a list, think about how it changes the list's structure and positions. Deleting an element in the middle shifts all later items, which can break code that depends on specific index positions. If you remove by value, decide whether to delete only the first match or every occurrence, such as when cleaning duplicates. For more complex situations, it can be safer to build a new list that includes only the items you want, so your data stays accurate and consistent with your application's needs. Python code, removing list elements. This lesson focuses on how to remove elements from a list in different ways and what happens to the list each time. You will see how to delete items by their position, by their value, and by checking a condition. As you compare these removal methods, you will observe how the list's structure and contents change. The goal is to help beginners learn safe and clear ways to update dynamic lists while avoiding common mistakes. In this part of the code, we point out that no extra installations are needed because we only rely on Python's built-in standard library. The operations we perform, such as working with lists, are fully supported without any external packages. This keeps the setup simple and ensures that anyone can run the code using just a normal Python installation without worrying about additional dependencies. We begin with a list of seminar attendees that serves as our starting dataset. This list contains 6 names: Alice, Bob, Charlie, Dana, Evan, and a second person named Bob. We will use this list to explore and demonstrate different ways to remove elements from a list in Python. We begin by printing the original list of seminar attendees to establish a clear starting point. This initial display serves as a baseline before we make any changes. After we remove elements using different methods, we can compare the modified list to the original. This comparison helps us track how the list changes and understand the effect of each removal method. We use the pop method to remove an attendee from the list at a specific position, in this case, at index 2. This method updates the list by taking out the element at that index and also returns the removed element. We then store this returned value in a variable called removedByIndex. This is helpful when we need to know exactly which item was removed, especially if the order of the list matters, or we plan to use that removed attendee later in the program. After removing an attendee by its position in the list, the program shows the updated list and also prints the name of the person who was removed. This confirms that the correct element was taken out and makes it easy to see the change. Together, these outputs help you verify that the list has been modified as intended. The code removes the first occurrence of the name Bob from the list of attendees by using a remove operation that searches for and deletes the first matching entry. This change happens directly on the original list, so no new list is created. It is a simple way to delete a specific value when you already know it is present in the list. When we remove the first occurrence of the name Bob from the list and then print the list, we see that only that first matching entry is deleted, while any later ones remain. This shows that the remove method affects just the first match it finds. It is useful when you want to delete a specific item without knowing its position in the list, but you should remember that it only removes the first instance of that item. We begin by creating an empty list called cleaned attendees, which will store only the names we want to keep. This empty list acts as a fresh container that starts with nothing in it. As we go through the original list of attendees, we will add names to this new list only if they meet our rule of not being named Dana. In the end, cleaned attendees will contain just the approved names that passed this filtering step. We go through each name in the attendee list one at a time so we can decide whether to keep it or remove it. During this loop, we check if the current name matches Dana. If it does, we leave it out. If it does not, we keep it. In this way, the final list contains all attendees except those named Dana. The code goes through each name and checks whether it is different from Dana. If the name is not Dana, it is added to a new cleaned list. As a result, Dana is removed from the original collection and only the remaining names are kept. The code displays the final list of attendees after removing any entries with the name Dana. This illustrates how to filter a list based on a specific condition. By excluding all matching names, the example shows how the list is cleaned to include only the remaining attendees. This script shows several ways to remove elements from a list of seminar attendees. It first displays the original list, then removes an attendee by position using a method that also returns the removed name. Next, it removes the first occurrence of a specific name using another list method. Finally, it builds a new list by looping through the original and adding only the names that do not match a given one. After each operation, it prints the updated list to illustrate how the list changes. Searching list elements. When working with lists, an important task is checking whether a value is present and finding where it appears. This lets you confirm things like a student's enrollment before recording grades or verify an item in a shopping cart to avoid duplicates. In these cases, you are only querying the list for information, not changing it. By asking whether a value exists, how many times it appears, and at which positions, you can guide your program's decisions without manually scanning every element. When working with a list, you often start by checking whether a value is present, such as seeing if a keyword appears in a blog's tags or if a flight number is in a schedule. After confirming that the value exists, you may need to find its exact position so you can do something with it, like changing the order of a task in a priority list. In survey data, locating the first time a particular answer appears helps you connect it with related information, such as the respondent's demographics or the time the response was recorded. When searching through lists, repeated values and missing values can both be important. You might count how often a temperature appears, or see if it only occurs at certain times. And not finding an error code in logs can show that a type of failure never happened. By combining search methods with conditions, you can trigger actions when items are missing, filter out certain entries, or summarize how often events occur. This makes searching a powerful tool for gaining insights and supporting decisions in your programs. Python code, searching list elements. In this lesson, you will work with simple lists by searching for values and understanding where they appear. You will learn how to test whether a value is in a list before trying to use its position, which helps avoid errors. You will also practice finding the index of a value and counting how many times a particular value occurs in the list. Together, these skills give you a basic toolkit for safely and effectively searching lists. In this part of the code, we point out that you do not need to run any pip install commands. The example relies only on built-in Python features, so no extra libraries or packages are required. Everything you need is already included in a standard Python environment, which keeps the setup simple and ready to use. We begin with a shopping cart list that contains several items, including apple, banana, apple again, orange, and banana again. This list is designed to simulate a cart with repeated items so we can practice searching within it. Because it includes duplicates, we can later focus on finding the first time a specific item appears and counting how many times it shows up in total. We begin by choosing the specific item we want to look for in the list, such as banana. This chosen item is then used to check whether it appears in the list. Once defined, it also lets us perform tasks like finding its position or counting how many times it occurs. By setting this item as a separate variable, we can easily adapt the code to search for different items just by changing its value. To check whether a specific item is in our shopping cart list, we use the in operator, which gives a true or false result. If the item is present, the operator returns true. If it is not, it returns false. This quick membership test tells us whether it makes sense to continue with other actions, such as finding where the item is in the list or how many times it appears. This code checks whether the item we are looking for, in this case banana, is in the shopping cart list, and then prints a message to the console. It uses the result of the membership check, stored in a variable, to decide what to say. Based on that result, it clearly tells us if banana is present in the cart or not, giving immediate, human-readable feedback. To work with an item in a shopping cart list, you first check whether the item is present. If it is, you then find its position using the list's index method, which returns the position of the first matching item. This position is given as a zero-based index, meaning counting starts at 0. You can then use this index for any further operations you need to perform on that item. The code finds the first position of an item in a list and then adds 1 to that index before printing it. This adjustment is made because Python lists start counting positions at 0. By adding 1, the result matches the way people normally count positions, starting from 1 instead of 0. This makes the output more intuitive for users to understand. To find how many times a specific item appears in a shopping cart list, we use the count method on that list. We give it the item we are interested in, and it returns the total number of times that item occurs. This tells us the frequency of that item in the list, which can be useful for tasks like inventory tracking or data analysis. This code prints a message that tells you how many times a specific item appears in the shopping cart list. It combines the item's name with the number of times it occurs to form a clear, readable sentence. This gives you quick feedback about how frequently that item shows up in the cart and helps you understand the cart's contents at a glance. Now we will search for an item that is not in our list. We set a variable to the text value grapes, which represents an item we know is missing from the shopping cart. This lets us test how the program behaves when the item being searched for does not exist. By doing this, we can clearly demonstrate how the code handles a search that fails to find a match. To check whether the item named grapes is in the shopping cart, we use the in operator, which returns a true or false value. It gives true if grapes is found and false if it is not. We then store this result in a variable called missing exists so we can easily refer back to whether grapes is present later in the code. we display a message to report whether the item we are searching for, grapes, is in the shopping cart. This message includes the item's name and the result of the membership check stored in the variable that holds whether it exists. In this way, the output clearly indicates if grapes are present or missing from the cart. This example shows how to search and count items in a Python list using a simple shopping cart. It first checks whether a specific item, such as a banana, is in the list using a membership test. If the item is found, it reports the position of its first occurrence using human-friendly numbering and counts how many times it appears. The script also checks for an item that is not present, like grapes, and confirms its absence. Overall, it demonstrates how to efficiently test for membership, find positions, and count repeated items in a list, while avoiding unnecessary operations. Looping through lists. Basic for loops. A basic for loop is used when you have a list of items and want to perform the same action on each one. The loop visits each element in turn and assigns it to a loop variable so you can process it. This might involve printing each item or checking a condition for each value. By handling the movement from one item to the next automatically, the for loop lets you focus on what you want to do with each element rather than how to step through the list. A basic for loop lets you work with each item in a list one by one without manually tracking positions. For example, if you have a list of cities, the loop automatically selects the first city, lets you perform an action like making a note, then moves on to the next city. This process repeats until every city has been handled. Because the loop manages the sequence for you, the same simple structure works well for both small lists and large datasets. Basic for loops are a fundamental tool in everyday programming for working through lists of items. They let you handle each element in turn, apply some operation, and then move on to the next. This simple pattern is used in many tasks, such as organizing responses, processing orders, or examining data. By mastering this looping pattern, you gain a flexible way to perform many kinds of list operations and prepare yourself for more advanced techniques. Python code basic for loops. In this lesson, you will practice using basic for loops to go through simple Python lists. You will see how the loop visits each element in the list one by one. As it visits each element, the program will print a short custom message that includes that element. The focus is on keeping the examples clear, simple, and easy for beginners to follow. This comment explains that you do not need to run any pip install commands, because the script only relies on Python's built-in features. In other words, it does not use any external libraries. This keeps the code simple, easy to run, and accessible on any standard Python installation. We create a list called Cities to Visit that holds 3 city names: New York, Chicago, and Los Angeles. This list represents the places we plan to travel to. By storing the cities together in one list, we can easily go through them later to print travel messages or plan our itineraries. We use a loop to go through each city in the list of cities to visit. For every city, the program prints a message that says we want to visit that city this year. This shows how to iterate over each element in a list and include that element inside a formatted message. The result is a personalized travel message for every city in the list. We begin by making a list of 4 numbers that represent the daily high temperatures in degrees Fahrenheit. Each number in this list stands for the high temperature on a different day. Later, we will go through this list one value at a time to print a brief weather summary for each day's high temperature. We use a loop to go through each value in the list of daily high temperatures. For every temperature, we create a short sentence that states the high for that day in degrees Fahrenheit. We then print each sentence, producing a simple, day-by-day summary of the weather. This ensures that every temperature in the list appears once in the output. This script shows how basic for loops work in Python by iterating over 2 different lists. It first goes through a list of cities and prints a short message about wanting to visit each one within the year. It then loops through a list of daily high temperatures and prints a brief weather summary for each value in degrees Fahrenheit. Overall, it provides a simple example of using loops to process lists and generate customized output for each item. Using enumerate. When you loop through a list, you often need both the item and its position, such as when working with survey responses or ranking movies. The enumerate function helps by automatically pairing each element with its index. This removes the need for a separate counter, makes the loop easier to read, and reduces mistakes that come from managing indexes by hand. The enumerate function pairs each item in a list with its position, starting from 0, and gives you both the index and the element as you loop. This makes it easy to modify items based on their position, record where something occurs, or create numbered output. For example, you can quickly label students as Student 1, Student 2, and so on, without counting manually. In a time series, it similarly links each reading to its time step, which helps organize and analyze the data. The enumerate feature lets you loop over items while also keeping track of their positions. And you can choose any starting number instead of being forced to start at 0. This is helpful when you need numbering that matches real-world expectations, such as beginning multiple choice questions at 1. It keeps the loop index aligned with your desired numbering while still clearly tracking positions. In data processing tasks like cleaning product lists or analyzing logs, this makes it easier to locate where problems occur and supports more expressive, reliable loops. Python code using enumerate. Use the enumerate feature to get both the index and the value from a sequence at the same time. First, show how it naturally counts from 0, which is the default indexing. Then, demonstrate how to set a custom starting index so the count begins at 1 instead. Finally, use this to print a numbered list of students where each student is labeled with a friendly, 1-based position. The line with the pip install command is just a placeholder comment, indicating that no extra libraries are required for this example. It tells anyone reading the code that everything needed is already included in standard Python. This means there is no need to install external packages, which keeps the setup simple. Overall, it serves as a clear reminder that the code runs in a clean and straightforward environment. We begin by creating a list of student names: Anna, Bilal, Carlos, and Dana. This list serves as a simple example to show how we can work with both the position and the value of each item. Later in the code, we will use a tool that lets us access each name along with its index in the list at the same time. We loop through the list of students using the enumerate function so we can access both each student's position and name at the same time. Enumerate counts positions starting from 0, so the first student has index 0, the next has index 1, and so on. For each student, we retrieve this 0-based index along with the student's name. We then print a message that shows both the index and the name together, making it easy to see each student's position in the list. We print a blank line between sections of output to make the results easier to read. This visual separation helps distinguish one part of the output from another. As a result, users can more easily follow and understand the different sections of the printed results. We use the enumerate function on the list of students and set the starting index to 1 so the count is more natural for people to read. In each loop, enumerate returns 2 values that we unpack into a position and a name. The position holds the current index beginning at 1, and the name is the current student in the list. We then print a message that combines the position and the student's name, producing a clear roster that shows each student's place in the list starting from 1. This script shows how to use the enumerate function to get both the index and the value of each item in a list of student names. It first loops through the list using the default 0-based index, printing each index with the matching name. Then, it repeats the loop but starts counting at 1 to create a more natural, human-friendly list of positions. This demonstrates that enumerate can be customized to begin counting from any integer, which is useful when you do not want to use 0-based indexing. List aggregation basics. When you loop through a list, you can combine its elements to produce one meaningful result. You begin with an initial value and update it as you visit each item. By the end of the loop, this process lets you calculate things like a total cost, a highest score, a count of items, or an average rating based on the entire list. To sum values in a list, you start with a total of 0 and add each item as you loop through the data. For example, you can add up monthly electricity bills to find the total cost for the year. The same idea applies in many situations, such as turning daily sales into quarterly revenue, or daily step counts into weekly totals. In each case, the loop visits every data point, and the aggregation step combines them into one meaningful overall result. Aggregation with loops is not only about adding numbers. It also lets you build new collections or summaries from a list. For example, you can filter survey responses to keep only those from people above a certain age or with specific keywords. You can also process a list of words to count how often each one appears, helping you find the most common terms, or combine pieces of text into a single report. In every case, the loop visits each element, and your aggregation rules transform them into a useful structure for analysis or communication. Python code, list aggregation basics. Use a running total pattern to add up values in a list of monthly electricity bills. A loop goes through each bill one by one and adds its amount to a cumulative total. After the loop has processed every bill, the final total represents the yearly electricity cost. Print this final total to show the complete annual expense. This line is simply a placeholder comment, indicating where you would add a command to install a library if the script needed one. It serves as a reminder to make sure all required dependencies are installed before running the code. In this particular script, no external libraries are actually needed, so the comment is mainly there to support good practice for scripts that might require additional packages in the future. We begin by creating a list that stores the electricity bill for each month of the year, with one value per month. Each value is an integer measured in dollars, representing that month's cost. Having all 12 monthly bills in a single list makes it easy to go through them in order. This structure lets us quickly calculate the total electricity cost for the entire year. We start by creating a variable to store the total cost for the year and set it to 0. This gives us a clear starting point with no charges counted yet. As the program processes each monthly bill, it will add that amount to this running total. By the end, this variable will hold the complete yearly cost. To find the yearly electricity cost, we go through each monthly bill one by one and keep a running total. For every bill, we add its amount to the total accumulated so far. We continue this process until all monthly bills have been included. The final value of this running total is the total electricity cost for the year. The program calculates and prints the total electricity cost for the entire year in dollars. It does this by showing a short message followed by the value that represents the sum of all monthly bills. This final result gives a clear summary of how much was spent on electricity over the year. This script adds together all the monthly electricity bills stored in a list to find the total cost for the year. It starts with a total of 0, then goes through each bill and adds its amount to the running total. After all the bills have been processed, the script prints the final yearly electricity cost. When you run it, you see one number showing how many dollars were spent on electricity over the entire year. In this lecture, you learned to create and manipulate Python lists using indexing and slicing. Use common list methods to add, remove, and search for elements. And iterate over lists with loops to process each element. In the next lecture, Lecture B, we will go over tuples and dicts.
Thank you for your attention. See you all in the next lecture.